degree 4 have other variation. That means, in fact, if you look formally at the dimension space of local variation, is 20. That was first, I think, observed in the more modern language by Kodaira, that in fact, having a surface, very nicely given surface by a question of degree 4, you can vary a complex structure in such a way that the manifold won't become projective. So you add parameters, one parameter, it's not a question now, it's just a formal parameter of deformation, and then you obtain something which you, I would say, cannot even describe. There is no good way to describe it somehow. We know invariance, but to place it somewhere in nature, there is no way to place it as into a projective space, as a complex operator. Okay, so, and in particular, in that case, the theory of local variation is kind of perfect. So, so we have a quadrant. So essentially, we have a space x squared equals to 0 in H2 S. Now I shall say S for the surface. S to C, S is complex coordinates. So we have this kind of quadratic equation, x squared equal to 0. And then we consider the x bar. We have a complex structure, a condition greater than 0. So we have a kind of a natural space of variations for such varieties is kind of piece of quadratic in space so it's a quadratic in space P21. Yes. So we have this space. We have projectivization because x modulo equation. And inside this quadratic, we have the action. So so here we have a sublattice H2Z, and we have the following structure. So inside this space, we have kind of, so these are all kind of infinite number of hyperplane sections, very dense number of simple hyperplane sections, and these sections, so the points of these sections correspond to projective surfaces of different degree. And many of them are isomorphic, but isomorphic surfaces correspond to the orbit of group satisfying this form. That's called 319 Z, acting on this. Okay, so I want to explain. So this is a picture of the space, yes? So of the kind of global description of projections. But it is not one-to-one. So there are many points which actually dense numbers of points corresponding to the same surface, but given by different projective embedding, even for projective surfaces. So divisors here correspond to projective, projective. And maybe I shall say what is degree. In projective geometry, in order to get an embedding of a surface into a projective space, you need a line bound. Essentially, you want one line bound on projective space. O1 is a standard line bound on a projective space. So projective space is corresponding to a set of line, and then it gives O minus 1, but dou is O. And then if you have L on S with many sections, then you map into projectivization of H0 of S. So by varying this line bundle L, and this is discrete set inside the R, we can obtain different embeddings. And degree of L is equal to C1 L squared. This is Chen class, and this is image 4. So points, kind of the same points, equivalent points on different devices, correspond to different line boundaries. So there is a, I would say, from each divisor, if we consider a subgroup here, corresponding to a given divisor, we obtain some kind of variety parametrizing surfaces with a given line bound. So if I fix degree 4, then we obtain a nice algebraic variety parametrizing such surfaces. But this group is too big. So the quotient here, the action is almost every derivative. So there is no good space parametrizing, that's good analytic space, parametrizing different, separating different orbits, different different complex Kessler surfaces. Okay, so this is about general Kessler surface. What about surfaces with Lagrangian fibration? And surfaces with Lagrangian fibrations are given by another everywhere dense set of intersection. I don't want to say parallel even, hyperplane sections, which corresponds to the property that there is divide d squared equal to 0, which is an element. It's approximate, it's very approximate answer. So we have kind of surfaces with additional element. So we have, for example, if we have a projective surface, that means we have a line bundle with positive degree, which has many sections and therefore provides an embedding. It happens in case of Kessler surfaces that if you have extra device with square 0, then you have an elliptic fibration. So, and basically for any such a divisor, you can organize an elliptic fibration. So the geometric sense of such a divisor is that if you have divisor, is basically you can view it as a class of a line bundle, but in that case also as a class of a curve. And here the class of D is this fiber, the square of a fiber is 0, and as it happens, and this is a very particular case of Kessler surfaces, you have a D, anything D square equal to 0, so line bound with a class equal to 0, and non-trivial, you have elliptic fibration. So it may be, I'll say, there is a small thing here, but you always have such a fibration. Maybe it's different class, but. So I just want to give a picture. And certainly this case of Kessler surface is an ideal case of hyperkahler manifold. And the whole theory of hyperkahler manifolds, since its invention, was try to prove analogous results for all hyperkahler graphs. Okay, do you have questions at the moment? Because if you understand that, then it is easy to kind of proceed. Because what we are doing now is basically trying to make another.
Excuse me, why does this condition reduce the dimension to 18?
Well, it just, you see, dimension to 18 because you have a divisor here. Yes, it gives codimension 1. So the total space is dimension 20. Yeah?
That's okay.
We have a one condition for manifold to have a line bundle with C1L greater than 0. So this is,
Right.
yes, so this is, so you have a line bundle